Good morning, ladies and gentlemen. Today we are going to talk about the next part of thermodynamics, which is about the kinetic theory of ideal gases. I apologize for not being dressed as professionally as usual, but it is a Friday. Now, last year you talked about ideal gases a little bit in chemistry, but when we talk about kinetic theory, we're going to go into this a little bit more in depth. And let's just recap about the kinetic theory first. There are four main assumptions that the kinetic theory has about ideal gases. The first assumption, of course, is that gas particles themselves are extremely tiny. So any of these gas particles that are floating around not only are tiny, but they're so tiny that they are very, very far apart from each other. So even though you have this entire space here filled with millions and millions of gas particles, they're so tiny that they're still extremely far apart, and that's what this animation is representing. The second assumption is that these balls that are flying around, these molecules that are flying around, well, they exert no forces on each other except during collisions. What I mean by no forces, I mean that there's no gravitational force between any of those two particles. Okay, there's no sort of attraction, nothing electrostatic, nothing gravitational. We'll just assume since it's such a negligible amount, we'll assume it to be zero. In real life, of course, there are interactions and there are other forces, but for now, for an ideal gas, we'll assume that there aren't. Also, we assume that all collisions are elastic. That means as each of these balls collide with each other, there's no loss of kinetic energy. And of course, that the kinetic energy of the molecules themselves are directly proportional to the temperature. Meaning, if I increase the temperature of the gas, I increase its kinetic energy, and it's directly related. So let's just write that all down quickly. The four main assumptions of the kinetic theory are gas molecules are small and far apart from each other. They exert no forces on each other aside from collisions. We also can assume that all these collisions are elastic, which means, of course, that there is no loss of kinetic energy, and that this kinetic energy is directly related to temperature. Okay, so those are the four main assumptions of kinetic theory of ideal gases. Now, let's talk a little bit more about that fourth assumption, about the relationship between temperature and kinetic energy itself. So, the formula actually looks like this. Kinetic energy of a single gas molecule is equal to 3/2 Kb, which is the Boltzmann constant, we'll go over that in one moment, times temperature. The Boltzmann constant is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. That is a value that will always be given to you. Now, but because this is joules per Kelvin, that means whenever we are talking about temperature, then we have to make sure that the unit is in Kelvin as well. And ultimately, since this is kinetic energy, we get the unit for this is going to be in joules. So basically, if you double the temperature, you double the amount of kinetic energy that gas molecule has. Now, side note here, the thing is, if we actually have a new formula for kinetic energy, and that's the kinetic energy of a single gas molecule, how exactly does that relate to our old formula? Well, the fact is, since it does solve for kinetic energy, we can set both formulas for kinetic energy equal to each other. And if you set them both equal to each other, well, what we ultimately can do is we can solve for the velocity. So the velocity of the average velocity, or really the root mean square velocity, which is the same thing as the average velocity for the most part, of a gas molecule is equal to radical 3 times the Boltzmann constant times temperature divided by the mass. And we'll practice using that in a moment. Okay? So just keep note of that. Notice here, if I double the temperature, I do not double the speed. Rather, if I double the temperature, I increase the speed by radical 2 because of this radical sign over here. And that is a very common question on the AP. Okay. So now, in this practice problem over here, they ask, what is the average translational kinetic energy of molecules and gas at 37 degrees Celsius? So, very basic, where we understand that this temperature is in degrees Celsius, so we have to convert to Kelvin. So we plus 273, and we convert to 310 Kelvin. So therefore, the formula is kinetic energy is equal to 3/2 kBT. So equals to 3/2 times 1.38 times 10 to the negative 23rd joules per Kelvin times 310 Kelvin. The kelvins will cancel out, and we're left with the unit joules. And we end up with 6.42 times 10 to the negative 21st joules. And you might be thinking, well, that's not very much. It's an extremely tiny number, and that's true. It is an extremely tiny number. But we're talking about one gas molecule, one teeny, 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 tiny gas molecule. If we were to solve for how fast that gas molecule is, well, I could then use the formula that we manipulated before. The velocity, the root mean square velocity of a gas is equal to radical 3 kb times t over m. Or I could set this equal to 1/2 mv squared. I could solve for the speed. Now let's assume that this molecule, which is not stated, is helium. Helium has a mass of 6.46 times 10 to the negative 27 kilograms. So if you plug that in to whether you plug it in at the bottom over here or you plug into this formula, we'll just plug into this one for now, so it's equal to radical 3 times 1.38 times 10 to the negative 23rd joules per Kelvin times 310 Kelvin divided by 6.46 times 10 to the negative 27 kilograms. We get that the average speed, the root mean square speed, is equal to 1,409 meters per second. So that means at just a little bit above room temperature, a helium gas molecule, on average, is zipping around at 1,400 meters per second, which is about 3,000 miles per hour. Now, the thing is, even though helium is going at on average 3,000 miles per hour or 1,400 meters per second, are all the gas molecules actually going at that speed? No. As you guys can clearly see in this demonstration again, or in this animation, some are going slower, some are going faster. But on average, they're all going at a certain speed. And that's what VRMS means, the root mean square speed. It is the average speed of the molecules. So let's try another problem. On the next page, we have a question about a nitrogen molecule, and they're asking about what's the average translation of kinetic energy. So if we use the formula again, kinetic energy is equal to 3/2 kB times T. Of course, the temperature has to be converted into Kelvin, so that's going to be 293 Kelvin. It's simply 3/2 times 1.38 times 10 to the negative 23rd joules per Kelvin times 293 Kelvin, and we get a total kinetic energy of 6.065 times 10 to the negative 21 joules. Now, notice, did I actually use any of the information about nitrogen yet? No, because it doesn't matter what kind of gas it is. Any gas at that temperature has the exact same kinetic energy. However, they don't all have the same speed. Okay? So in this case, when we solve for speed, we'll actually deal with the mass of nitrogen. And nitrogen is naturally diatomic. The molecular mass of a nitrogen molecule, if you guys remember from chemistry, the atomic number is 14. The atomic mass is about 28. So 28 times 2 is equal to 56 atomic mass units, which is approximately 9.3 times 10 to the negative 27 kilograms. So now, if I set this equal to 1/2 mv squared, or if I use the original form, V RMS is equal to radical 3 kBT over m, I will find that the average velocity of nitrogen would equal to 1,142 meters per second. Okay. If it was a hydrogen molecule, then it would be much faster. If it was something like radon, which is a very large, heavy gas molecule, the speed would be significantly slower. Okay, so speed depends on the mass, but all gas molecules have the exact same kinetic energy at a given temperature. The next part of the question simply asks us, well, what if you have 1,500 nitrogen molecules in the gas? Well, in this case, if you're just looking for a total of 1,500 gas molecules, then it would just be 1,500 times the kinetic energy of one gas molecule, which you had previously solved to be 6.065 times 10 to the negative 21st. So in this case, we just multiply it with a nice, easy answer of 9.098 times 10 to the negative 18 joules. Okay? So this is just to help you understand that this formula, 3/2 kBT, solves for one gas molecule only. If you want more, you simply just multiply by the number of molecules. But what if you have a mole of nitrogen gas molecules? If you hopefully remember from chemistry what the definition of a mole is using Avogadro's number, 1 mole is equal to 6.02 times 10 to the 23rd molecules. Okay, so it's literally just another number. It's something similar to if I would say, how many are in a dozen? Well, in a dozen, we automatically know that the number is 12. In a mole, we automatically know that the number is 6.02 times 10 to the 23rd. So in this case, if I'm looking for a mole of molecules and how much energy that has, well, that'd be 1 mole, or Avogadro's number, Na represents Avogadro's number, times the energy of one molecule, the kinetic energy of one molecule, which was 6.065 times 10 to the negative 21st joules. You get the total energy of 1 mole of nitrogen gas to be 3,651.13 joules. Okay, So that's just a brief review to recap Avogadro's number and number of moles. But what if there are 2.5 moles? If there are 2.5 moles, then, well, that's just simply taking 2.5 times Avogadro's number, which is 6.02 times 10 to the 23rd, right, times the kinetic energy of a single gas molecule, and ultimately you would get a total energy of 9,128 joules. Okay, so hopefully you understand this kinetic energy is always the kinetic energy of a single gas molecule. Now the thing is, I want to show you guys how do you solve for the entire gas load. Is there a faster way to solve for the entire gas of the energy of the entire gas? Well, normally when we do 2.5 times n times Avogadro's number times kinetic energy is really the 3/2 times the Boltzmann constant times the temperature. And that would give us our number of 9,128 joules. But what I want you guys to know, scientists have already realized, well, if you combine the Boltzmann constant and Avogadro's number, they're both constants. So if you multiply 6.02 times 10 to the 23rd, and you combine that with the Boltzmann constant 1.38 times 10 to the negative 23rd joules per Kelvin, you actually end up with 8.31 joules per mole Kelvin, which is R. Okay? So whenever you combine Na, the Avogadro's number, and Boltzmann constant, you end up with the universal gas constant of R, which you saw before in the ideal gas law. So if I were to redo this just a little bit, that means the total internal energy, U, internal energy of the entire gas, is simply equal to 3/2 N, which is the number of moles, times R, which is the Avogadro's number, times the Boltzmann constant, times temperature. So if we had plugged in 3/2 times 2.5 moles times 8.31 joules per mole Kelvin times 293 Kelvin, we get the exact same answer of 9,128 joules. Okay? So this is just an alternate method of solving for the internal energy of the entire gas itself, rather than solving for the energy of one molecule. Next, we are going to talk about the transfer of heat. So if we're talking about transfer of heat, we need to actually define what heat really is. Because saying transfer of heat energy, that actually doesn't even quite make sense if you understand what heat is. You see, well, if we look at our definitions, internal energy we had defined as the total energy contained by the substance. If it was a gas, it would be U for gas. It would be U equals to 3/2 nRT. Temperature we had already defined before. Temperature is a measure of the average kinetic energy of the substance. But what's heat? Heat is literally defined as the transfer of energy itself. Okay? Heat is when energy goes from hot to cold. It's always going to be from a higher temperature to a lower temperature. So if you take a look at these two jars below, we have one large liter of a liquid at 80 degrees Celsius, and we have this tiny little beaker of another liquid at 95 degrees Celsius, which has a higher temperature. Obviously, this guy has a higher temperature. So if you were to combine those two jars and put them next to each other, heat energy would automatically flow from the higher temperature to the lower temperature. And we, by the way, we use Q to represent heat. Okay? But that doesn't mean it's, well, but if you look at question number 6, which jar of water can actually melt more ice? You see, just because something has a higher temperature doesn't mean it has more internal energy stored inside. Because in the end, this large container has a lot more internal energy than this little container over there. So if you were to put ice into the container, the larger container has more U. It has more internal energy itself. Okay? Heat transfer, Q, depends on high temperature, low temperature, but in terms of amount of energy stored, that depends entirely on how many molecules there are. And a large jar has a lot more molecules. Now, if I were to go back to here, talk about heat itself, we're talking about, again, the transfer energy. And there's actually a formula for that transfer energy. The formula for heat transfer is H equals to K A delta T over L. Let's actually bring it into an example so that way it'll be easier to understand. Okay. As I said before, the formula is H equals K A delta T over L. K, as you guys can see over here, is the coefficient of thermal conduction, meaning if you have a higher K, it's going to transfer heat much more quickly, as you guys can see through the number of arrows going through the tube. If you have a smaller K, heat transfers a lot slower. So metals usually have a very high coefficient, and plastics or other things that are insulators will have a very low coefficient. A is the cross-sectional area of the pipe, meaning it's literally how thick is that pipe. And if I were to increase the area of the connection, well, obviously there's a lot more heat able to transfer through. So if I make it a thicker and thicker area, I increase the amount of heat transfer. And of course, vice versa, with a smaller pipe, we have less heat transfer. Delta T is the difference in temperature. I already said that it goes from hot to cold. But the greater difference in temperature, the faster heat will actually go. Okay? So if you want to cool off a bowl of hot soup, for example, you could leave it out on the table, and it'll take a certain amount of time to cool, but if you put that hot cup of coffee into the refrigerator, it'll cool off even faster because there's a greater difference in temperature. L is length. It's literally how long is that connection between the hot and the cold. And if you move them closer together, it's easier for heat to transfer than when it's further apart. Okay? So ultimately, rate of heat transfer is based on these variables. But another way of saying heat transfer, H, is power. Because whenever we talk about the rate of heat transfer, we're talking about Q over T, or joules per second, or watts. So the unit for rate of heat transfer is watts, or joules per second. So literally, how fast is energy being transferred over? And that was basically our original definition for power itself. So now that I've explained the formula for rate of heat transfer, which is again H equals to Ka delta T over L, let's do a quick practice problem with an actual AP multiple choice question. So in this case, they ask, what is the rate of heat flow, H, between the opposite surfaces of a 3-meter thick cube of steel, in which the temperature on one side is 0 and the other side is 100 degrees Celsius? So I'm just going to draw it as a box for now, or as a square, and we see that it's 3 meters thick. This would actually be L. On one side, the initial temperature is equal to 0 degrees Celsius. On the other side, the temperature is 100 degrees Celsius. Now, because this is a cube, okay, so if I draw the rest of it as a cube, that means the area of this surface over here is going to equal to 3 times 3. So the area is going to equal to 9 meters squared. So now as I go through this question, I can solve for the rate of heat transfer using this formula, H equals Ka delta T. So H is going to equal to, they say that the thermal conductivity is 40 joules per meter second degrees Celsius. So H is equal to 40 joules per second meter degrees Celsius times the area, which is 9 meters squared, times the difference in temperature. Now, normally, of course, we want the temperature to be in Kelvin, but because this is a difference in temperature, delta T in Kelvin or Celsius is exactly the same. So we'll leave it as 100 degrees Celsius divided by the length of 3 meters. And that equals to 12,000 joules per second, or watts. Okay, so the answer in this case was choice B. And because the right side does have a higher temperature, overall the heat flow would have went in the left direction. So this concludes heat transfer, and the next unit, of course, is going to be the laws of thermodynamics.